Okay. Okay. Any questions from last time? So do you see lecture 11 SI425?
Yes, ma'am.
Okay, excellent. Okay, any questions from last time? Okay, I will take this silence as there are none. Okay. Okay. So last time, I think we ended our time by, so we proved this monotone convergence theorem, right? So let's just quickly recall the statement. So if xn is a monotonically increasing sequence of real numbers that is bounded above, then the sequence xn converges, and the limit of the sequence is actually the supremum of a certain set. Yeah, and what is this set? This set is, so let me write this set as E. This is the sequence, not the sequence xn, but viewing it as a subset of R. Okay. So what is this telling us? This is telling us, this is giving us a condition so as to guarantee when is a bounded sequence of real number actually convergent. Yeah, please recall, in general, a bounded sequence of real numbers need not be convergent, but this theorem is telling us that if you have a monotone sequence of real numbers which is bounded, then it is necessarily convergent. So I hope this makes sense to everybody. We provided a proof to this result, and we stated an analogous statement for monotonically decreasing sequences, and we saw an example, a very simple example of the sequence 1 by n. Okay, so the second example was 1 plus 1 by factorial 1 plus 1 by factorial 2 and so on. Yeah, so we applied the monotone convergence theorem to conclude that the sequence xn converges. So let's look at the third example, which we we could not finish last time. Yeah, so continuing from last time, so I'll just say more examples on monotone convergence theorem. Any point of time, any questions, please feel free to stop me. Yeah, so this is example 3, and in this example, I am considering the sequence xn defined as for each fixed index little n in the set of natural numbers, I am considering 1 plus 1 by n to the power n. Right? Okay. So what we will do, we will try to apply the monotone convergence theorem in order to conclude that the sequence converges. So we will show that the sequence is 1 bounded, 2 monotone, and hence convergent. Okay. So let's try to do that. So let's look at this. Yeah. So let's first try to prove that it is monotone. Yeah. So in order to that, let's look at the terms of this sequence. So I am going to apply the binomial theorem. Yeah. So applying the binomial theorem, we see that what do we see? We see that xn, which is defined as 1 plus 1 by n to the power n, is the same as you write 1 plus n choose 1 times 1 by n. So this is n plus n choose 2, which is n minus 1 by factorial 2, 1 by n square, plus n choose 3, which is n minus 1, n minus 2 by factorial 3, 1 by n cube, and so on. Yeah, and what would be the last term? The last term would be, so it would be n choose, yeah, so it will be n minus 1, so on 2 times 1 divided by factorial n minus 1 and 1 by n to the power n. Yeah, I hope this is okay with everybody. Yeah, this is binomial theorem. Okay, so I am going to write this in the following manner. What am I going to do? Okay, so I'm going to keep the first term as it is, and I'm going to divide the powers of n into the terms in the numerator. Yeah, so this term becomes 1. Now I'm going to retain 1 by factorial 2 as it is. I'm going to distribute this power of n into terms of numerator. So I will have n by n, which is 1, n minus 1 by n, which is 1 minus 1 by n. Correct? So likewise, the third next term would be 1 by factorial 3 as it is. N by n, which is 1, n minus 1 by n, which is 1 minus 1 by n, and n minus 2 by n, which is 1 minus 2 by n. Yeah? So continuing like this, what do I get? The last term would be 1 by factorial n, 1 times 1 minus 1 by n, 1 minus 2 by n, the product, and the very last term would be 1 minus n minus 1 by n. Okay, all right. So what is this? This is the nth term of the sequence xn, right? So if this is the nth term, then I can write down the n plus 1th term as well, right? In a similar fashion, yeah. So what will that be? The n plus 1th term would be, borrowing from our analysis upstairs, this would be 1 by factorial 2, 1 minus 1 by, this time n plus 1 downstairs, 1 by factorial 3, this is a factorial, yeah, 1 minus n plus 1, 1 minus 2 by n plus 1. So I will have an n plus 1 term in the denominator, right? So let's write it down. What will happen here is, so this is what I am writing as the second last term in the in xn plus 1. So this will be a 1 minus 1 by n plus 1, 1 minus 2 by n plus 1, so on, and 1 minus n minus 1, n plus 1. Yeah. You know, if this looks like a bit too much, don't worry. You know, all I'm doing is just writing down the terms, nothing else. Yeah. If you sort of write it down coolly on your own, you will get the same thing. So I'm writing down the last term in xn plus 1. This is just like the last term upstairs in the xn. This is given as 1 minus n by n plus 1. Is that okay? Yeah, so for the benefit of everybody, I'll just write it. So this is xn, the nth term, and this is xn plus 1, the n plus 1th term, right? So my goal is to say that this sequence xn is monotone, right? So I have to compare the terms xn and xn plus 1, yeah? So if you look at these two expressions here, xn contains n plus 1 terms, xn plus 1 contains n plus 2 terms, right? And each term in xn is less than or equal to the corresponding term in xn plus 1. And in fact, xn plus 1 has one more positive term. Conclusion, the sequence xn is increasing, correct? Is that okay? Yeah. So I would say that, I will not write that, I'll just say it follows from above that the sequence xn is increasing, that is, in fact, xn here is strictly less than xn plus 1, and this is true for each integer n, positive integer n. Is this okay?
Yes, ma'am.
Yes, is that okay? Yeah, all right, excellent. So what is that I have shown? That the sequence xn is monotonically increasing, right? So if you go back to the statement of monotone convergence theorem, in order to appeal to that theorem, we still need to assert that this sequence is bounded above, right? Bounded below is not a problem because these are all sequences of positive terms, right? So how do we show that this is bounded above?
Excuse me, ma'am.
Yes, please.
Ma'am, I lost my connection. Could you explain the xn plus 1, the last term?
See, last term, see, I'm just borrowing it from here. If the last term in xn is 1 by factorial n, over here it will be 1 by, so this will be 1 by factorial n plus 1.
Yeah, that was the
Yeah,
problem.
yeah, so sorry. Yeah, thank you so much for correcting me. Yeah, so this will be a factorial here. Yeah, this will be factorial, and I will have a 1 minus 1 plus n by 1, 1 minus 2 by, yeah, and everything else seems to be is all right. Yeah, is that correct? Yeah, thank you so much for correcting me.
Yes, ma'am. Yeah.
Okay, all right. Okay, what else? Now, how do I show that this is bounded? Yeah, again, I will look at this expression for xn which I have written here, the first line on this slide that you see at your end. So, xn is 1 plus 1 plus something, 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 right? So it is clear that, each of this term in the parenthesis, 1 minus 1 by n, 1 minus 1 by n, 1 minus 2n, these are all strictly less than 1. Yeah, so you just forget about them. So what I'm trying to say is that you can say that, so I will call this as something, yeah. So I'll call this as expression A, yeah, just to sort of, it follows from A that, what does it follow? Yeah, that the nth term xn is strictly less than, so you have a 1 plus 1. So, it's the same thing as xn plus 1, which you see here. So, is less than 1 by factorial 2. You just ignore the other terms, 1 by factorial 3. And I'm still considering only the nth term, so I will have only 1 by factorial n. And this is true for each little n in the set of natural numbers. Correct? Is that okay?
Yes, ma'am.
Yes.
Yes, ma'am.
And this was exactly the example 2 that we worked out, the right hand one. Yeah. So let me just go back just to refresh your memory. This was just example 2. So there we showed that the term on the right is bounded above, right? We use some a simple inequality to show that, right? So in fact, it's bounded above by 3. Yeah. So I'll just quickly borrow that here. Yeah. So this is in fact strictly less than 3 for all n in n, right? So this, I will not repeat that argument again. Conclusion, the sequence xn is monotonically increasing and bounded above. To conclude that the sequence xn is convergent. Is that correct? Is that okay? So I'm applying the monotone convergence theorem here. Yeah, we have shown that the sequence xn is monotonically increasing and bounded above, and hence it has to converge thanks to the monotone convergence theorem. And what else can we say? We say that the limit xn exists, and the limit xn, so I'll call it the limit of this sequence xn will be at most 3, correct? Because each term is at most 2, right? So in fact, one defines the limit of this sequence to be the Euler number E. Yeah. So the definition. So definition of the Euler number E is the limit of this sequence, right? So this is So what we showed upstairs was that the limit of the right hand side exists and is a real number. We have defined it as an Euler number 3. Yeah. So far what we know is that it is positive and it is at most 3, right? So one of you actually asked this question last time about why not use this. So I sort of wanted to talk about it once we had this example. Okay, so is this okay with everybody?
Yes, ma'am.
Yes. Okay. All right. So do I take it as a yes with everybody present here?
Yes, ma'am.
Yes, ma'am.
Okay. Excellent. All right. So I think before going ahead, let me take up one more example of one more example on monotone convergence theorem, because I think we've been sort of not doing any of examples and just stating results. So let's do one more. Yeah. So let's consider the sequence like this, defined like this. Yeah. So I'm defining it recursively. What is that I mean? So I give you what is x1. So I say set x1 as 1, and given x1 as 1, I say that let me define the n plus 1th term as the following. It is 1 plus xn by 2 plus xn. Yeah, so this is for n strictly greater than equal to 1. Yeah. Yeah, so this is called as the recursive definition of giving a of a sequence. Once you know x1, then you can plug in the value of x1. The output would be x2. Then x2, you can plug in x2. The output would be x3, right? Okay. So the question is, as before, is the sequence xn convergent? If so, what is the limit? If not, justify why it is not convergent, right? Okay. So sort of let's write down the terms of this sequence. So do a little calculation. X1 is 1 is given, x2 would be 1 plus 1. Yeah, so it would be 2 by 3. Correct? What would be x3? X3 would be 1 plus 2 by 3, 2 plus 2 by 3. What would that be? So this is 5 by 6. Is that correct? 5 by 8? Yeah,
Yes,
and
ma'am.
and things like that. Okay. All right. So I will sort of say that. So the first thing is to note the following thing. Yeah. So this is my claim that the sequence xn is decreasing. Yeah. So you already see that. Yeah. X2 is smaller than x1. X3 is smaller than x2. In fact, this is a pattern. Yeah. So I say that xn plus 2 is strictly less than xn plus 1. Yeah. So how do you prove that rigorously? How do you prove this statement rigorously, that this is true for this inequality holds true for each index n? How do you prove that? That xn plus 2 is less than xn plus 1 for each index n? How does one prove statements like this?
Now, can we use induction?
Yes, so one way is to one way is to use the principle of mathematical induction. Yeah, I hope everybody has seen that before. So I will just quickly write that here. Use the principle of mathematical induction to conclude the following. Is that okay? Everybody has seen that before?
Yes, ma'am.
Yes. Is that a yes with everybody present here? I'll say that to conclude that. Is that a yes with everybody present here?
Yes, ma'am.
Yes, excellent. Yeah. So
Yes,
I
ma'am.
will leave it to you to figure out that the sequence xn is actually decreasing using the principle of mathematical induction. Now, what else? In order to apply monotone convergence theorem, I need to show that the sequence is bounded below. Correct? But that is easy, right? It is evident that what is evident? that each term of the sequence is positive, right? Right from the definition, right? So this is bounded below, right? Which means that applying the monotone convergence theorem, it is easy to see that what is easy to see? It follows that the above sequence converges. The sequence xn converges, right? And so let's set x naught as the limit of the sequence xn, which exists, right? Now, can you evaluate x naught? Can you find out what is the exact value of x naught? So I will leave that for you to work out. Is that okay? Yeah. So how do you do that? You use the defining equation for the sequence in order to find out x naught. Is that okay?
Ma'am,
Yes, please.
can we do this by saying that xn plus 1 and xn will converge to same point? And
Xn plus 1 and?
xn will
Yes.
converge to same point.
Correct. Why does that happen? Why does the sequence xn plus 1 and xn? You are right. But we have talked about it, right? Because it's a tail of the sequence, right?
Yes,
Tail of
ma'am.
the same sequence, right? So use the fact and, plug it in this functional equation and you will get it. Is that okay? Does everybody follow this? Thank you so much.
Yes, ma'am.
Yeah, so I can leave this thing as an exercise for all of you. Okay, good. All right. Okay, so I will sort of, in that case, if there are no further questions on this topic, then I'll sort of like to move on to the next thing, which is subsequences. Yeah. Okay. What is a subsequence? Okay. So let's see. So let's start like this. Yeah. So here's a definition. Let xn be a sequence of real numbers. Yeah. Right. Which means this. And let's consider an increasing sequence of positive integers. Yeah. So consider, I will sort of emphasize on this a little later, but let me write it down. Consider, in fact, consider a strictly increasing sequence of positive integers. Yeah, strictly increasing sequence of positive integers. So what is this strictly increasing sequence of positive integers? So let me denote it by n1, strictly less than n2, strictly less than n3, and so on. Yeah. So each of these n1, n2, n3, and so on, these are all natural numbers. Yeah. Let me put the S here. Okay. Now what do I do? Now what will I do? In this listing of the sequence xn, I am going to pick the corresponding terms as determined by n1, n2, n3. Yeah, so I will say that then the sequence, which one? Xnk given by, so what are the terms of this sequence? xn1, xn2, xn3. Yeah? This is called a subsequence of the given sequence. Of the given sequence xn. Yeah? So what is that I am doing here? A subsequence, given a sequence xn, a subsequence is obtained by choosing terms from the original sequence without altering the order of the terms. Yeah, without altering the ordering of the terms. Yeah, so I'll give you an example. What is this I'm trying to say? Yeah, so suppose that let's consider example. Let's consider the sequence xn given by n plus 1. Yeah, right. So over here, you know what is x1? x1 is 1 by 2. Sorry, x2 is 2 by 3. Yeah, x3 is 3 by 4. And x4 is 4 by 5, and so on. Correct? Okay. So let me pick, n1 as 1. Yeah, I need to consider a sequence which is of strictly increasing positive integers. Yeah, and let me pick n2 as 3. Let me pick n3 as what do I want to do? So let me pick n3 as 5, and so on. Let me pick n4 as 7, and so on. Yeah, I go on like this. Yeah, and then what will my sequence be? So then my sequence xnk is to consider the sequence xnk, where what happens? xn1 is what? xn1 is x1 is 1 by 2, right? xn2 is what? It is x3, it is 3 by 4, right? xn3 is what? xn3 is x5, which is 5 by 6, and so on, right? So this is a subsequence of the given sequence xn. However, if you look at this, yeah, let me give you one more example. However, let's consider this. So let me consider this. Yeah. So if I consider 2 by 3, 2 by 3, 1 by 2, 3 by 4, 1 by 2, 4 by 5, then this is not a subsequence of the given sequence xn. Is this okay? Does everybody follow this? A subsequence is obtained by choosing terms from the original sequence without altering the ordering of the terms. In this example that I have written in red ink, the order of the term is altered, and hence this is not a subsequence. Is this okay? Does everybody follow this?
Yes, ma'am.
Yes? Okay. Very simple example. Okay. Very nice. All right. So what is that we need to do with subsequences? How do subsequences play an important role? So let's see. The very first thing is the following. So let's note down this observation, or let me call it a proposition.
Hello, ma'am.
Yes, please.
Ma'am, in this red, what you have written, if we remove 1 by 2, then it will become subsequence.
1 by 2 from everywhere, you know, not just the second.
Yes,
Yeah.
ma'am.
Yes.
Everywhere.
Yes.
Everywhere.
Correct. Then it seems like fine. Yeah. All right. Anything else?
No, ma'am.
Okay. All right. Okay. So let's fix this. Okay. So I'll write it as an observation. When you define a subsequence, given a sequence xn, when you define a subsequence, you write it as xnk. Yeah, that's the convention, right? The observation is now nk. You have nk as k is running over these set of natural numbers. Yeah, so nk is a sequence of natural numbers, right? The claim is that nk is always bigger than k. Why is that? So let's look at this. Now n1 is a positive integer. Yeah. So clearly n1 is at least 1, right? So there's no problem. Yes. Is that okay? Does everybody see this? So why is that? So let's look at k equal to 1. Now this is true, right? n1 is at least 1. Now look at n2. Yeah, the claim is to show that n2 is at least 2. Yeah. So how do we establish this? What is the only thing that we have fixed, right? All we know is that the sequence nk is a strictly increasing sequence. Yeah. So please note that I have a strict inequality here. Yeah. n1 cannot be equal to n2. n1 is strictly less than n2, right? So what does that mean? It means that, recall that n2 is strictly bigger than n1, which is at best, it is equal to 1. Yeah. So that follows that, what does it follow? It follows that n2 is bigger than 2, right? Is that true? Yeah. So what am I trying to say is one can use the principle of mathematical induction together with the fact that the sequence nk is strictly increasing sequence of natural numbers to conclude that the observation that I have made above holds true. Yes? Yes, so let me just write that down. Suppose that nm is bigger than m for fixed m, and in order to apply the principle of mathematical induction, you consider, what do you consider? You consider n subscript m plus 1. Yeah, now since the sequence nk is strictly increasing, the inequality nm plus 1 strictly greater than nm holds now, but this is bigger than 2, and hence it follows that n subscript n plus 1 is bigger than m plus 1. Yeah, and hence so I will just write use the principle of mathematical induction to conclude. Is this okay with everybody? Does everybody follow this little bit?
Yes, ma'am.
Yes?
Yes, ma'am.
Okay, excellent. Very nice. Okay. Okay. So if this bit is okay, then let's move on to the next thing. The next is I want to talk about this proposition. So let's run through a couple of statements and then perhaps we will be able to see some examples. This is the proposition. What is this? I want to say that so if xn is a sequence of real numbers converging to x, so unless stated otherwise, these are all real numbers, right? And if xnk is a subsequence of the sequence xn, then the proposition says that the subsequence xnk also converges to the same limit as the sequence xn as k tends to infinity. Every subsequence of a convergent sequence converges to the same limit. Correct? Yeah. So I hope the statement is okay with everybody present here. So let me try to illustrate the proof. So what do we do? So let's fix some epsilon. And let's remind ourselves what is that we are to prove. So you are given a convergent sequence xn of real numbers converging to x, and xnk is a subsequence of the given sequence, and you have to show that xnk also converges and to the same limit. Yeah. So what will we show? We are required to show that. Let me write it down. We will show that what happens corresponding to this epsilon, there exists a positive integer, let me call it n0, in the set of natural numbers, such that what happens, all the terms of the subsequence x and k live in, well, there's no x0 here, or maybe, I'll just quickly make this as x0. Yeah, so this limit I'm denoting as x0. So all the terms of the subsequence x and k live in epsilon neighborhood of the point x0 beyond the stage n0. Correct? This is the meaning of the statement that the subsequence x and k converges to the limit to x0. Correct? Is that okay? Okay, so let's see how do we go about it. Yeah, so how do we go about it? What is that we are given? We are given that the sequence xn converges to x0. So let's write that down. Let's unwind what is given to us. So since the sequence xn converges to x0, corresponding to this epsilon that we are given, there exists a positive integer. So there exists a positive integer which I am denoting by capital N, such that xn minus x0, this distance is at most epsilon beyond the stage capital N, right? Is that okay? Yeah, so there is a cutoff beyond which all terms of the sequence are in the epsilon neighborhood around the point x0, right? Is that okay? Everybody with me up till this point?
Yes, ma'am.
Yes. Okay. Now I want to prove that x and k, satisfies this. So what is that I want to do? I want to apply this. So let me call this something. So let me sort of call this as this statement as the last thing that I just wrote as inequality 1 here. Well, statement 1 here, right? So what is it I want to do? I want to apply this to x and k's. Yeah, I want to make a similar statement about x and k. So in order to do that, I want to show that nk must be as big as capital N, right? I need that information, right? But how do I do that? Yeah, how do I do that? So here's one trick. Almost follows from the definition. So I'll just recall that nk is bigger than k for every index k, right? So we're given this subsequence x and k, and I'm saying that nk is at least k for all. Yeah. So what will I do? So I look at the following notation. Yeah. So let's see. So I say that if little k is bigger than capital N, what is capital N? Capital N is the cutoff that I get by convergence of the sequence xn to x0. If little k is bigger than capital N, it follows that what follows? Now, n subscript k is bigger than k is bigger than capital N, right? Right? Which means that, which means what? Sorry, I just happened to scribble my pen here. Unintentionally though. Okay. So what am I trying to say? So if little k is bigger than capital N, where capital N is the cutoff in statement 1, it follows that nk is bigger than capital K is bigger than capital N, and hence one can appeal to statement 1, and hence it follows from 1 that it follows from 1 that what follows? That x n k minus x naught is less than epsilon whenever k is bigger than n. And that's it. We are done. Is that okay? I will pause for a minute because I think this is the very first sort of proof that we are seeing in sequences. Does everybody follow what is happening and why are we doing that?
Yes, ma'am.
Yes? Is that a yes with everybody present here? Everybody with me up till this point?
Yes, ma'am.
Yes, ma'am.
Excellent.
Ma'am,
Yes,
I did
yes.
not understand from the inequality that nk is greater than or equal to k is greater than or equal to n.
See. So if so, look at this. Yeah, nk is always bigger than equal to k. Yeah, we sort of observe that, right? So
Yes,
I am choosing if little k is bigger than this cutoff capital N, then the following inequality will follow, right? The first one, nk is bigger than k, always is true, and I am choosing capital little k such that I'm just considering all those little k's which are beyond the stage capital N. That's it. And why am I doing this? I am doing this because I am interested in applying statement 1, which holds true only for integers bigger than capital N. Correct?
Okay.
Yes? Yes, that's the only reason I am doing this. Right?
Okay. Okay.
Yes, that's the only reason I am doing this.
Yes.
Okay. Okay. All right. So, what is that we have proved? That every convergence sequence of real, so every subsequence of a convergence let me say that again. Every subsequence of a convergence sequence of real numbers converges and converges to the same limit, right? So if you want to say that, for example, a sequence xn of real numbers does not converge to a point x naught, it is enough to produce a subsequence of that sequence which does not converge to x. Correct? That is one way to go about it, right? Is that okay? Because all subsequences of a
Yes, ma'am.
convergent sequence must converge to the same limit. Okay. Any questions here?
Ma'am,
Yes, please.
in this proof, we considered k greater than equal to capital N. If it
Correct.
is greater than equal to capital N,
Yes.
we can say that it will converge from that M tail of sequence, that definition.
No. See, I'm just saying, what is the meaning of the statement that a sequence x and k converges, right? So let's look at this. So let's just look at this. So in order to show that a sequence x and k converges, I need to find out an index n naught such that beyond the stage n naught, that serves as a cutoff. If you look at terms of the sequence xn n naught, xn n naught plus 1, all of them must live in epsilon neighborhood of the point x naught, right? So I am just trying to get hold of this index n naught.
Okay.
Yeah. And how am I doing that? I am using the fact that the sequence xn converges to x naught. So that gives me some cutoff capital N. Now I want to show that terms of the sequence x and k, also satisfy that, right? So for example, let me try to draw a picture here. So let's say, so if this is in the number line, this is capital N, right? This is this capital N, this cutoff, right? Now, so you have a number, so I will have an n minus 1 here and so on, right? Now, 1, 2, 3. Now, but what is that I am given? I am looking at N1, N2, N3, N4, N5, N6, like that, right? So subsequence Xnk is indexed by Xn1, Xn2, Xn3, Xn4, Xn5. Now, I can apply this inequality 1 only if the index Nk is bigger than capital N, right? Is that okay?
Yes.
Yes. Now, in order to ensure that Nk is bigger than capital N, one way to go about it is this. All I want to make sure is, my goal is to make sure that Nk is bigger than capital N, right? That's what I want to do in order to apply inequality, in order to apply statement 1. Now, all of this is an arrangement in order to make sure this, what I've written in green circle, that holds true. Is that okay?
Yes.
Are you still lost?
No, ma'am.
Yeah, because we have no control, N1 may not be 1 and N2 may not be 2. N2 may be, for example, 600 and N3 may be 601. We don't know. And N3, so N3 may be very different from 3, for example, right? I want to make sure that at some stage, the terms of the sequence X and K are sort of in epsilon neighborhood of the point X naught.
At some stage, not for all of them.
Some stage onwards, for all k bigger than n naught. Yeah, some stage onwards, isn't it? That's the sort of definition of convergence, right? Yes. Beyond the stage n naught, all of them should lie in this neighborhood of x naught. I hope I am able to sort of understand your question correctly.
Yes.
Yeah, is that okay?
Yes, ma'am.
Yeah. Anybody else has a question on this? Let me see how many of you are here. So 34 of you. Yeah.
Ma'am?
Yes, please.
No, I have a question.
Please go ahead. Yeah.
Ma'am, the converse of the statement may not be true, right? Always?
The converse is not true. Yeah. Not at all. This is only one-way implication. all subsequences of a convergent sequence converge and converge to the same limit.
Yes, ma'am.
But if all subsequences of a convergent sequence converge, does the sequence converge? In fact, there's a question to this effect in the assignment that I have posted. I think assignment number 4. Yeah, please try that out. So your question, yeah. So if every convergent subsequence of a sequence converges, does that mean the sequence converges? Yeah. So the converse may not be true.
Okay, ma'am.
Yeah, but I don't want to sort of give away the entire thing, because I want you to think about that question. Please try that. There's some joy if you sort of discover things on your own. So I just write that down in sort of language. What is that saying? Conclusion: all subsequences of a convergent sequence converge to the same limit. This is what we have shown upstairs, yeah. Any further questions on this? Okay, so I believe there are no further questions. In that case, let's go on. So there's something interesting that I want to consider next. Okay. So is that a yes with everybody? Shall we go on? Everybody with me up till this point?
Yes, ma'am.
Yes, is that a yes? Okay, good. Very nice. All right. Here is another interesting result next. Okay, bear with me, and let's just see these results, and then hopefully we will be able to take up some interesting applications. Okay, what is that we want to say next? So again, this is a statement about sequence of real numbers, because this concept doesn't make sense otherwise. So the next statement is about existence of monotone sequences. Right? What is that I want to say next? So given any real sequence xn, there exists a monotone subsequence. Let me write that down. The proposition and how it is relevant, we will also see that. Let xn be a sequence of real numbers. I will say that the statement is, then there is a subsequence of the sequence xn. So this is a subsequence of the sequence xn that is monotone. So what is that we are trying to say here? That every real sequence admits a monotone subsequence. Yeah, so every sequence of real numbers admits a subsequence that is either monotonically decreasing or every real or monotonically decreasing. Yeah. this is sort of rather useful. And how and why, maybe we will be able to discuss that once we are sort of at home with the proof of the statement. Yeah, but does the statement make sense to everybody? Yeah. So the sequence xn in itself may not be monotone. Yeah, I am not saying that every real sequence is monotone, right? The sequence xn may not be monotone. It may not be monotonically increasing, need not be monotonically decreasing, but it necessarily has a subsequence that is monotone. That's what this is saying. So is this okay? The statement, is this okay with everybody present here?
Yes, ma'am.
Yes. Okay. So bear with me and let's try to cook up a proof. Yeah. No, anybody who is little bit uncomfortable about the statement, please feel free to stop me. Yeah. Okay. Okay. All right. So I am given the sequence xn of real numbers. I have to construct a monotone subsequence, right? So let's see. I say that let's look at the following set. Yeah. So what is this set? Let me call it as, I'm going to consider all indices little n such that the mth term xm is strictly less than xn for m bigger than n. Yeah. So let's look at what is this set doing. Right? So what is this set doing? What is this set doing? It is collecting all those indices little n such that xn, the corresponding term in the sequence, xn is bigger than any term that follows it in the sequence. Is that okay? I'm deliberately pausing. So is that okay? Does everybody follow what is the set capital S saying?
Yes, ma'am.
Yes. Is that a yes with everybody? Everybody with me up till this point?
Yes, ma'am.
Yeah. So it's a collection of all those indices little n such that the corresponding term xn is bigger than any term that follows it in the sequence. Okay. Now there are two possibilities, right? One, the set S is finite, and two, the set S is infinite. Yeah. So let's look at there are. So I'm going to investigate both of them one by one. Both the scenarios one by one. So case one is if the set S is a finite subset of the set of natural numbers. Correct? And the other scenario would be, what if the set S is infinite? Okay, so let's look at that. Let's look at this case when the set S is finite. Okay. Now, what is S? S in this, in case one, is a finite subset of natural numbers, right? So you just, it's a finite set. You can take the maximum and you can find. So which means that I can find a natural number capital N such that what happens? Such that K is less than equal to capital N for all k in S. Yeah. So what is capital N? Capital N is the maximum in here, right? I'm using the fact that S is finite. Correct? There are only finitely many terms. You just take the maximum of all of those, call it capital N. Is that okay?
Yes, ma'am.
Yes. Remind yourself what is that we are trying to do. We are given a sequence xn. Our goal is to construct a monotone subsequence of this given sequence xn. Yeah. Okay. Now, having fixed capital N, let me pick something which is bigger than capital N. Right. So let N1 be strictly bigger than capital N. Now, if N1 is strictly bigger than capital N, then clearly by definition, N1 cannot belong to the set S, right? Yeah, so let me draw a little picture here. Yeah, so this is, let's say, this is my set S. So this is the set S, and so in this point is, let's say, capital N, and N1 is somewhere here, right? N1 is strictly bigger than capital N. Yeah, so clearly by definition, the way we have chosen capital N, N1 cannot be an element in S. Now, by definition, if N1 is not in S, the definition of N1, the definition of the set S guarantees that there exists some index, let me call it N2, there exists N2 bigger than N1 such that what happens? Such that Xn2 is bigger than Xn1. Because if not, if there is no such index N2, that would imply N1 is in S, which is a contradiction. Correct? Is this okay with everybody? The last statement that I wrote down here is just from the definition of the set S. Yeah, so in this picture here, N2 is somewhere here. Yeah, sorry. Is this okay? Everybody with me?
Ma'am, could you please explain the last sentence again?
So I'm saying that since N1 is not in S, yeah, N1 is not in S, you look at the definition of the set S, yeah. N1 is not in S means that there must be an element N2 bigger than N1, such that if you look at X of N2 and compare that with X of N1, the inequality would be Xn2 must be bigger than or equal to Xn1, because if not, if there is no such N2, then that would imply that N1 is in the set S. But that cannot be the case because N1 is strictly bigger than capital N, right?
Okay, ma'am. Yeah.
Yeah, is that okay?
Yes, ma'am.
Yeah, please don't get lost in indices. All I'm trying, you see where am I heading? I am trying to construct a subsequence of Xn. So what that I'm trying to do is I am trying to construct a strictly increasing sequence Nk. Yeah, I want to get hold of N3 bigger than N2 bigger than N1. Now, the next stage is I want to find N3. Correct? Is that okay?
Yes, ma'am.
Yes. Is that a yes with everybody present here?
Yes, ma'am.
Yeah. Okay. All right. So let me sort of do that one more time. So note that what is that we have done above? We have found N2 which is bigger than N1, but N1 is bigger than capital N, right? It follows that since N2 is bigger than capital N, it follows that the index N2 cannot belong to the set S. Correct? Now again, bootstrapping the argument, applying the argument one more time, what we used above, it follows that, what follows? It follows that there exists some index N3 bigger than N2 such that If you look at xn3 and xn2, xn3 must be bigger than or equal to xn2, right? So continuing in this manner, you get a strictly increasing sequence of positive integers. I'll just write that down. Continuing in this manner as described above, one finds a strictly increasing sequence of positive integers which is the strictly increasing sequence nk of positive integers such that what happens? Such that at each stage xnk plus 1 is bigger than equal to xnk for each k index k. Right? So what is this is saying? This is saying that we have been able to construct a subsequence xnk of the given sequence xn, which is monotonically increasing. I'll write that down. So here xnk that we just constructed is a subsequence of the given sequence xn. So in fact, it's a monotonically increasing subsequence. That is, so I'll just sort of reword what I've written. So here we have been able to construct a monotonically increasing subsequence of the given sequence xn. Is this okay so far with everybody?
Yes, ma'am.
Yes? Okay, so if that is a yes with everybody present here, then we look at case 2. Yeah, so far we only looked at the case where S is finite. It's also possible that S is infinite, right? Everybody with me up till this point? Yes. Yes. Any questions, please ask, 33 of you here. Yeah. Okay. So since there are no questions, let me proceed. So the second scenario is if S is infinite. Yeah. Okay. I'll just write that the definition of S one more time because it's not on this side. Recall what was S. S was this collection of, this is a set of all those indices such that xm is less than xn for m bigger than n, right? Xn is bigger than any term that follows it in the sequence. Okay. Now we are under the assumption that you have an infinite set S. Okay. Now what do we do? Again, you have to construct a subsequence of xn, which means that you have to get hold of a strictly increasing sequence of natural numbers nk first, right? Okay. Now, so S is a subset. S is an infinite subset of natural numbers here. So I will say that the first thing that we notice that S has a least element. Yeah. So let N1 be the least element of S. We have not talked about it. How do we assert that n1 exists? This is what follows from, perhaps some of you have seen, this is the well ordering principle. It says that every infinite subset of natural numbers has a least element. So I'll write that down. Use the well ordering principle. So have you all heard about it? So this was the very first reading assignment that was handed out to all of you. So this is
Yes, ma'am.
yes. So this is in. Let me sort of tell you where is it exactly in this book. So this is 1.2.1. 1.2.1 of Bartley and Shepard. Yeah, this is a property. Yeah, so there's no proof. You assume that this is true. That every non-empty, sorry, not every infinite subset of natural numbers has a least element. Yeah, in fact, you don't even need infinite. Every non-empty, yeah, I was right. Every non-empty subset of natural numbers has a least element. So let me write down at least the statement here for clarity. Those of you who are seeing it for the first time, every non-empty subset of natural numbers has a least element. So if this non-empty subset is finite, there's not much to be done. This is a property which is sort of non-trivial for only an infinite subset of natural numbers. Okay, all right. So anyways, the upshot of this is that little n1 exists. So what do? Now you look at the set S minus n1, right? So you have the set S. N1 is the least element of the set S, and I'm now looking at S set minus N1, right? Now what you do, this is again another infinite subset of natural numbers. You apply the well ordering principle one more time and find the least element of this set now. Yeah, so I'll call it let N2 be the least element of this set, right? And so on, yeah. And you continue in this fashion. So what do you get? You have a listing of S. So continuing in this manner, we have a listing of the set S. So if I tell you to compare N1 and N2, what can you say about N1 and N2? N1 is the least element of S and N2 is the least element of S set minus N1. So what can you say about N1 and N2?
N1 little than N1.
N1 is less than N2, right? Correct? Yes? Is that true? Yeah. And the second stage, sorry?
N2 is greater than N1. Yeah.
Yes. Yes. Right. Right. And you continue in this manner. So you will get N1, N2, N3, and all of these N1, N2, N3 are elements in S, right? All of them belongs to S. Correct? Is that okay? Yeah.
Yes.
So let's recall that, and I'll just sort of emphasize that since nk minus 1 is an element in S for each index k, and nk minus 1 is strictly less than nk by construction, what follows from the definition of S is, what if now you can say something about x nk minus 1 and x nk. It follows from the definition of S that xnk minus, so which terms do I want to control? Xnk and xnk minus 1, yeah? So this would be true. Am I right? For all k, yeah, x and k would be strictly less than x and k minus 1. This is just from the definition of S. Yeah, so upshot of all of this discussion is that here we have a subsequence xn k of the given sequence xn, which is monotonically decreasing. Let me just write that down. This is a monotonically decreasing subsequence of the sequence xn. And that's all. I am done with this proof. I will pause if any of you have questions. So is this okay with everybody present here? No questions? Any questions? Yes,
Ma'am,
please.
in this
Yeah.
monotone sequence,
Please
hello?
tell. Yes, tell me.
Ma'am, we are not talking about convergence of xn and its subsequences, anything like.
See, the statement of the theorem is here that there is a subsequence of xn that is monotone. We are not bothered about what happens to the convergence. We'll come to that little later. That would be the next statement.
Okay, ma'am.
Yeah, that's interesting question, very relevant, but this proposition does not address that question. This proposition only addresses if there is a monotone subsequence of the given sequence xn, and it says yes always.
Okay, ma'am.
Correct?
Thank you. Yes, ma'am.
Any other questions? Okay. So shall I assume all of this material is okay with everybody present here?
Yes, ma'am.
Yes. Is that a yes with everybody present here? Okay.
Yes, ma'am.
Yeah, okay. So every real sequence admits a monotone subsequence. Yeah, this is what this proposition says. Now, this proposition is very, very important because of the following result, right? See, this is a long-standing question, right? So let me try to say. So what is that we know? So every convergence sequence is bounded, right? This is that we know is bounded, right? This is true. But what about the converse? Every bounded sequence is convergent?
No, ma'am.
No, correct? So this is no, right? So I'll just mark it with red.
No.
This is not true. Yeah, this is not true. This is a false statement, right? Okay. So we cannot expect a statement saying that a bounded sequence of real numbers is convergent, right? So the next best statement would be to show that a bounded sequence of real numbers admits a convergent subsequence, right? The next best thing on this planet would be that a bounded sequence of real numbers admits a convergent subsequence. The sequence itself may not be convergent, but some subsequence of this bounded sequence is always convergent. Is that okay? So this is a theorem. Yeah. So, so this follows as a consequence of what we did just now, but in the interest of time, I will sort of postpone this discussion to next time. But there are a couple of things that I want to sort of say. One, please spend time on the proof of this result that we just discussed. Seems like there is some discomfort about this proof. Yeah, so please read the proof of existence of monotone sequences on your own. Try to fix any sticky points, if any. Right. Number two, I have been observing, so this is the fourth assignment that I have submitted. Each time the assignment deadline is over, I see many emails in my inbox that, some things or the other happened and you are not able to turn in the assignment in time. Please understand, you get a little more than a week all the time to work on the assignment problems. Please do not keep pending till the last moment, and then because of some internet connectivity you could not submit in time. Next time onwards it will be a very strict deadline and I would not make any exceptions. In fact, if this trend continues, every time you send me 5 emails saying that something or the other happened and you could not send it on time, then I will be forced to introduce a penalty that -2 if the assignment is late by a day or things like that. Yeah, so please keep that in mind. Okay, I think with that I will just stop this for now, and so I'll just stop the recording. If there are any questions, please ask.